Okay, good evening, geometry students. Today we're taking a look at section 10.8, which is the geometric probability. First of all, let's define what geometric probability is. Well, let's actually define what probability is. Probability is the chance or likelihood that something will occur. Now, if something can't occur, then we say it has a 0% chance of happening, or zero probability, or as a decimal, that would be 0.00. If it for sure will happen, then the probability is 100%, or 1. Now, every other probability is always going to be a number between 0 and 1. And the reason why that's the case is the way probability is created. Probability is always a fraction. Probability is always the ways of getting what you're interested in or what you want divided by the total possible ways, okay? So we're always going to have a denominator that's bigger than the numerator or equal to, and therefore probability can never be a number more than 1, because how can you have more than the total possible outcomes that you're given? Now, in this course, what we're going to be interested in is something called geometric probability. And geometric probability will be a fraction, where in this case, we're going to take a look at the length or the area that I'm interested in and divide that by the total length or area to get my probability. Now, let's just jump into some problems. Let's look at this first one. This says, find each probability. So I'm starting at -3 on this number line and ending at 7. And I've got these letters representing each point on the number line. So this notation right here says, find the probability of finding, or if suppose I randomly picked just a dot, right? If I closed my eyes and I said, put a dot on the number line, boom. What's the chance or the probability that this point would land on the segment from H to U? Or in other words, what's the probability of getting the length from H to U? Well, how long is it from H to U? Well, let's see here. Here's -2, and my pen doesn't want to work. Here's -2. U is 4. So the length or the distance of HU would equal 4 minus -2. That's always how we find the distance between two things. We subtract them. So in this case, that length is 6. So since probability is always a fraction, I know that HU equals 6, and I know the total length from -3 to 7, well, that's 10. So the probability that I would pick a point that was between H and U will be 6 over 10, which reduces to 3/5. Okay, so the probability that I would pick a point that's between H and U would be 3/5. To do the probability that something is between E and T, well, here's E, here's T, so let's see here. Let's get rid of some of this stuff right here now. Okay, so to find the probability of getting a space between E and T, the first thing I need to do is find the length of ET, which would be, let's see here, from E to T, let's see, T is 3 units and E is 7, so 7 minus 3 would be 4 units. That's the length of ET. And we've already established that the length of WE, or the whole problem here, is 10. So the probability of getting a point that's between E and T would be 4/10, which reduces to 2/5. Okay, and there's some examples of some probability involving segments. Now let's take a look at some areas. In this problem, I've got a square where I have 4 circles that are all touching just at one point at all places, right? I'm told that the length of this square is 8, and I want to find the probability that if I randomly picked a point that it would land in this blue area, somewhere in this blue area, all right? Well, to do these problems, we probably want to come up with a game plan before we actually start doing the math. So the way I look at this, the only shapes that I recognize here are, I recognize that I've got a square, and recognize that I've got a circle. Now, my idea will be to get the area of the shaded, what I call ash. I'm going to take the area of the square, and I'm going to subtract the area of 4 circles. So I'm going to take the area of one circle, and that's the symbol for circle, and I'm just going to multiply that by 4 because those are 4 congruent circles. Okay? So let's jump on in here now. To do this, I'm going to start with the square. The area of the square would just be side squared, so 8 squared, which would be 64. And now I'm going to do the area of the circle. Well, I know the formula for a circle from the last section is pi r squared, correct? So now I've got to find that radius. Well, if you think about it, isn't the whole length of the circle, of the square 8? And I've got 2 congruent circles in here. Doesn't each one of these circles have to have a diameter of merely 4? But wait, if each circle has a diameter of 4, doesn't that mean my radius has to be 2? So I know then the area of my circle, let me get rid of some of these dots. So the area of my circle, guys, would just be pi times 2 squared, or 4 pi. So I know that the area of the shaded region would equal the area of the square, which is 64, minus 4 times the area of one circle, which is 4 pi, which would end up being 64 minus 16 pi. And if you think about this, isn't pi a little bit more than 3.14? And 16 times 3 is 48. So 64 minus 48 is 16. And so somewhere a little less than 16 would be that shaded area. But now I need to find the probability. So I'm going to get the probability of the shaded area, well, I'm interested in the shaded area, so he goes on top. And I want to put the area of the total shape on the bottom. Well, we calculated the probability of the shaded region, or the area of the shaded region, to be 64 minus 16 pi. And if you think about this, isn't the total area just this outer square that we've already found the area of? So we're divided by 64. Now here's some algebra that we get to focus on. Ladies and gentlemen, if I have 2 numbers that are added or subtracted in the top of a fraction, and they're both being divided by a single number down here, I can rewrite this as just the first number divided by the denominator, and then minus, whatever that sign is, minus the second number divided by the denominator. And when I do, I can reduce this. This becomes, well, 64 divided by 64 is 1, minus, and remember, pi isn't a variable, but he behaves like a variable. So I'm allowed to reduce when I'm multiplying 16 pi times 64, or when divided by 64, I can simplify the 16 and 64, and that would just become pi over 4. So the probability of landing in the shaded region would be 1 minus pi over 4. Here's an interesting question. What do you think the probability of landing in one of the circles would be? Next problem. Okay, last problem. Now I want to find the probability of getting in the shaded area in this problem, where you can see that I've got a circle circumscribing an inscribed equilateral triangle. So again, the first thing I need to do is I want to create a formula for that shaded region. So I think the area of my shaded region in this case will be the area of my circle minus the area of my equilateral triangle. So I got to find the area of the circle first, which is pi r squared And you can see from the picture that the radius in this circle is 6, so it'll be 6 squared. So the area of that circle is 36 pi. Now that was the easy part. Now let's take a look at this equilateral triangle. Now, when I do an equilateral triangle, what I like to do is if I'm given this radius, I like to extend it to create a full-on altitude where this is also the circumcenter of that, I'm not the circumcenter, the centroid of that altitude. And so I know that there has to be a 2-to-1 ratio between this length here and this length here. So if this length is 6, that has to be a 3. You guys remember that? Now, I also know that this altitude will take this 60 degree, 60 degree, and 60 degree equilateral triangle, and it'll split it into a 30, 60, and 90 triangle. So, I now know that I have a medium side of this equilateral triangle having a length of 9, and I need the length of this short side right here. Well, remember, to go from the medium side to the short side, you divide by radical 3, and if you did that, you would find that that would be 3 root 3. But if this piece is 3 root 3, doesn't this piece also have to be 3 root 3? So the whole length of that base would be 6 root 3. And now I'm ready to find the area of my triangle. The area of my triangle would equal 1/2 of the base, which is 6 square root of 3, times the height, which is 9, which would just be 27 square roots of 3. Okay, to get the area of the shaded region then, I'm just going to do the area of the circle minus the area of my triangle. And then lastly, to get the probability of the shaded region, I'm going to take the area of the shaded region, which was 36 pi minus 27 radical 3. Good Lord, that looks like a pi. I did not mean that to be a pi. My bad. And then divide that, guys, by the area of the outer shape, which is the circle, which would be 36 pi. And if you reduce this by making two fractions, well, 36 pi over 36 pi would be the first fraction, minus 27 square root of 3 over 36 pi would be the next fraction, which would make that just 1 minus, well, 27 and 36 can both be divided by 9, so that would become 3 root 3 over 36 divided by 9 is 4, and then pi. And so that would be the probability of landing in this shaded region. That's all for now. Talk to you later.